So today we're going to go through some more statistical tests. We've done statistical tests in the past. Can you name some of the tests that we did? So what are some of the statistical tests that we talked about in the past? The Z transform, which was the testing for what? Outliers, and the Dixon's Q-test, also an outlier. And then T-test for what? Equal means, yeah. And then F-test was for the variances, how wide the distribution is. So we have some other kinds of tests here. This is some of the screenshots today are from Minitab. So you can get Minitab on the campus computer. You can also download a free trial that will take you through the rest of the semester, so you can play around with that on your own. I would highly recommend it. And so here's some of the data. You know, we did that trainee versus the forensics chemist, and we were doing all of that in Excel, and that's fine. It was a good exercise to figure out those formulas, especially like the T-table formula and the F-table formula. But if you were to just grab that trainee data and go up in Minitab and do the graphical summary of statistics, this is what you get, and it gives you everything to you in one shot. You don't have to type in any formulas, and you get all of these things like the mean. So you have all of these great data points: the mean, the standard deviation, the variance. It shows you they have 10 data points, but it's even showing you that this was an outlier. So it did an outlier test on that one. And when you get that little asterisk, it's saying that doesn't fit within this population probably. It also shows the histogram of the data and then puts this normal curve on it. And it tests to see if this distribution is normally distributed. So they have this Anderson-Darling normality test. So it's giving you this p-value for normality. So if you are looking at any of these things like this normality test, I mean, the name normality test seems to tell you what it's doing, right? It's testing to see if the data is normally distributed. But you know, I don't know anything about Anderson and Darling. And so how would you find this out? Well, in Minitab, you just go to the help, and there's a stat guide on there. That's a really good stat guide. You can learn a lot of statistics just by going into Minitab and reading some of the tutorials and looking through the stat guide. So this is what you would do in the future if you had access to Minitab, or if you could get your company to buy it. You know, there's lots of things that we don't cover, and you can improve your understanding of statistics through this program. So if you click that, then you get this. So again, the help in Minitab and even the help in Excel on the different formulas is pretty good. So sometimes software help is garbage. You know, they say click file and open to open a file. Well, I could have figured that out, you know, but sometimes the help is really good. Gaussian's help is good. Excel's help is good, and so is Minitab's. So here's the Anderson-Darling normality test. So our null hypothesis is that the data follow a normal distribution, which kind of comes from the name, right? Normality test. Just like the T-test for equal means, the null hypothesis is right there, equal means, or equal variances for the F-test. That's the null hypothesis. And then the p-value is, of course, the probability that that's true. And if it's less than 0.05, then you can reject that null hypothesis. So we're going to call the data normally distributed even if there's like a 6% chance that it's normally distributed. There's not really anything magic about a normal distribution, but the normal distribution means that your calculation and your tests, like your Z-test for outliers, is based on a normal distribution. But if your data is not a normal distribution, then you've got kind of a mismatch in your statistics. And you can compute that Anderson-Darling test for other distributions too, but this is the graphical summary is including the normality test. So here's the forensic chemist. This distribution is not normal, so that normality test gives a p-value of 0.017. And we can see that, you know, all of the data points. I think there were 4 data points here. There were 3 data points here. And then 1, 1, and 1. And so you can kind of see that this data, if I were to plot the actual curve, it would look like this. And that's what we call a positive skew. This is the high numbers, low, and we can see that number right here. So this this analysis, this graphical summary, tells you if the data tails to the high numbers or tails to the low numbers. So we would also say it tails high. So I don't understand really how to, I guess I just came up with a good analogy because I've been watching the Book of Boba Fett, you know, and so this kind of looks like Jabba the Hutt, okay, blah, 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 okay, and he's looking at you. Where does his tail go? His tail goes high, okay. So a skewed distribution looks like one of the Hutts, okay. Pick your favorite, and that whichever side the tail is the thin part. Very good. So I'm going to have to use that forever now. This is the first time I've ever used that analogy. So if you're not a Star Wars fan and have no idea what Jabba the Hutt is, go ahead and just Google that. Okay, we don't need to get off track. Otherwise, I'll really get pulled off. Okay. Now, the trainee, this graphical summary has a kurtosis. It's talking about kurtosis here. That's a new word. Sounds like bad breath, but that's halitosis. This is kurtosis. Okay. So this is some property of this distribution has a high kurtosis, and so we need to look that up. So if we go to the Minitab stat guide and look up kurtosis and skewness, we get these two entries. So here's the kurtosis entry from the stat guide. This is another way that our distribution could be messed up. Now, the skew value tells you whether it's symmetric left and right, but notice how both of these are still symmetric left and right, but they're not normal. So you have this mirrored image right down the middle, and you see the left and right still look similar, so they're not asymmetric. But there's something problem with this distribution. And this is one of those situations where you might have two data sets buried within the same distribution. You might have a data set that has got a big standard deviation and a data set that has a narrow standard deviation. You see how you could have two populations in this grouping of data, one with a really narrow standard deviation, one with a really broad standard deviation. You could come up with a number of ways you might get that kind of data. Maybe something changed. Maybe you were using a real unreliable pipette for some of the samples, and you just weren't paying attention and picked up a more reliable pipette. And so some of the samples had a really narrow standard deviation, and other samples had a really wide standard deviation, but the mean was the same. And so then that's what you would end up with. Is this sharply peaked bimodal distribution. Okay, then maybe you could have multiple peaks that overlap. Like you might have, say, a Gaussian peak here, and then another one that's slightly shifted, and another one that's slightly shifted. And so you might have three distributions in there that aren't resolved, and maybe even some saturation of your signal. That's not a normal distribution, right? A normal distribution doesn't look like that. It's not flat top. Okay. And so that would be a negative kurtosis value if you had flat topped data. So if your histogram looked like this in the bottom, then you would have a negative kurtosis value. It might indicate that you have some, I would call it saturation of your data. You know, the data's going up and then your signal or number of data points are not coming in as what you imagine they would. You know, it's not normally distributed. Okay, so that's kurtosis. Now let's look at skewness. We talked a little bit about that with Jabba the Hutt. And so here's the entry value for skewness. So a positive skew is right skewed if the values are sorted left to right, in increasing value. So yeah, so I would say positive is skewed to higher values, right? So if the high values are on the right, then it's right skewed. But right and left can be misleading, because what if your values are plotted backwards, right, with the high values on the left? Then you would not get the positive skewness in that case with a right skewed distribution. So it depends upon which way the data is plotted. So if these are high values and low values, then this is right and left. Okay. And the negative skew is left skew or low value skewed. So this is a claim here. It says salary data is often skewed in this manner because many employees make relatively little, while a few people at the top in the management positions have very high salaries. Failure lifetime data is often left skewed because most of the items last a long time, but there's a few early failures because of some defect, but the majority last quite a while. And so we've got some examples of that. So let's look at some of those. Here's the salary data. I just went on Google and typed in, distribution of household income, and this is what I got. Now this is a histogram. Let's dig into what we have here. We've got these right here are called bins. And so we take all of the salary numbers, and of course, some of those, they've got decimal places. They're down to the penny, right? And so how do we get them into these blocks? We have bins, and we throw all of the numbers of salaries in the different bins, and they have, in this case, we have $5,000 bins. So that's the increment at which we increase our bar chart. Every bar is 5,000 more. So we have under 5,000 here, then 5,000 to 9,999, and then 10,000 to 1499, and so on. And so each different bar is the next bin of 5,000. This y-axis is percent of households. So it's been normalized. So you notice the maximum is slightly over 6%. Since it's been normalized, the whole area equals 100%. Okay. Yeah, you can read that. Okay. One thing I would like to point out that this most probable one is called the mode. So the mode of this data is 15 to 20,000. I'll put a K in there. 15 to 20,000 is the mode. That's the most probable household income at this particular year. I think it says 2011. Okay. This is the median household income, roughly 50,000. So that's the middle data point. If you were to sort all of the salaries from high to low, the middle one is the median. And then it doesn't show the mean, but the mean is somewhere up here. So the mean is always higher than the median if there's skewed data points. So say the mean is 65,000. And then you get up here, the bins, we're still doing $5,000 bins here, but then they lump the last two. This is a 50,000 bin. So right here, because the data is skewed out so far that if we included it all with 5,000 bins, there'd be a lot of bins of 0 or 1, and then it would just really go on for a lot longer. It goes up to over 250,000. What that would do if we were to plot that on the same plot would squeeze all of these down to where it was hard to read them. And so a lot of times they'll do this. They'll put some big bins at the top with really skewed data and lump all of those greater thans into those bins. And so it looks strange, but that's because the bin size has changed. This is a $50,000 bin. Okay. And this is a greater than bin. Greater than bin. So greater than 250,000. So those add up about 2% each. So 4% of households have an income greater than 200,000 in this time frame. Okay. So I just show you this because it's a great example of skewed data. It's pretty standard. You're going to see this in companies. You're going to see this in countries. You're going to see this in states. When they report income data, it's always in this shape, this skewed to high values or right skewed data. And also I want to point this out too. So whenever people report mean or median incomes, it should be the median that they report, not the mean, because the mean is unrealistically higher. It's more probable to make the median income. Okay, so whenever you're looking at salary data, like in a company or in a location, say you're going to relocate to the Northeast, and you get the job offer or whatever, you say, well, what's the median income at that company? What's the median income in that state? Am I going to be able to afford to live in that city? Right? If you go to New York and they say that your salary is $180,000, you're like, yeah, because you're in Huntsville right now. That would go a long way. But you're in Manhattan, and you look at the median income in Manhattan, and it's probably 210. And you're like, oh wow, it may be more expensive to live there, and so you just need to look at that, and you want to look at median incomes. It's less probable that you'll make the mean income. The mode would be the most probable. And so, anyway, rarely have I seen the mode income posted. Most of the time it's median income. And you hear in the news, they talk about changes in the median income. Okay. Let's look at some lower skewed data or skewed left data. So this is the age at time of death. So kind of a lifespan data, right? And this was from 2013 from the Social Security Administration. And they have it broken apart by male and female. And so you can see that on average, females live a little longer than males. Okay. We also see that there's maybe multiple modes here. So this may be multimodal data. So this would be the mode for the male age at death. So these are the modes, right? The medians would probably be somewhere here. And then the average or the mean might be somewhere here. Okay. But notice this little shoulder here. Okay, this has me worried. I'm 53, so there's a little bit higher probability of me expiring here this part of my life, 55 to 65. See that little shoulder there? Yeah. And then look at this. This is kind of funny right here. This is not really funny, but that little bump of 20 to 25. That's when they're dumb, right? That's also like car insurance, right? So for guys, car insurance is more expensive until they're 25. Because notice the rates are about equal there, 25 and above for men and women. But this bump, so for car insurance, that right there, that's the car insurance bump. They're just going straight on statistical data. And it's insurance, it's risk-based. So they're just looking at the risk analysis and saying, we're probably going to have to pay out on guys driving, so we'll probably just keep their rates a little bit higher to cover the risk. So this is how those decisions are made. Again, they're making decisions based on the numbers. Okay, and then down here you have So this lowest bin, again, is going to be a less than bin. And so that would be like infant mortality. Okay. Any questions about this data? Now, if they didn't break it into groups like male and female, then they would have multimode data here. And even the male group seems multimodal. Like there's more than one distribution. So that's what I'm saying. There's probably a distribution in here like this of the risky categories. And then there's probably a again, a skewed left distribution there that has a mean, a mode, a mean, and a median. And then there's the main group here. So each one of those has a different mode. And so that's why it's called multimodal. You don't have one population, you have distinct populations. Now, they're not totally resolved, but you have a subset of males that are adrenaline junkies and get in car wrecks and die. Okay, in Texas. No, that's what has been the joke. They put black boxes in Jeeps for years. Do y'all know this? It's a joke, actually. They put black boxes in Jeeps, and they recorded the last words said before a fatal crash. Okay, just like the airline things. And so you know where this is going. In most states, it was, oh my gosh, and they crash and die. And in Texas, it's hold my beer. So, yeah, sure enough. Okay, now skewness value doesn't always catch non-normal data, right? And so neither one of these has a strong skewness value. They're both symmetric. So remember, skewness just to test whether your distribution is symmetric or not. The left side looks like the right side. And so this down here is bimodal. It's got two modes. You've got a group here that's sort of pegged at your lower limit, and you've got a group here that's pegged at the higher limit. And so this is multimodal. So mode 1 and mode 2. But because those are fairly equal and it's symmetric on both sides, it would have a zero skew value. So here's again, just discussing that multimodal data. Here's a couple of very evenly distributed or even populations, meaning the same number of individuals or groups or data points in each distribution. And there's two modes here, two medians, two means. But if you didn't know that it was multimodal and you just calculated the mean and the median and didn't do a histogram or anything like that, you would have a misleading mean and a misleading median, because it would show you this middle point as the most probable or the one data point that represents the whole distribution, when really there should be two distribution data points that would represent it. You've got a large chunk of data here and a large chunk of data here. So these would be the most probable data values. If these data values were all in a sack and you were reaching in, you would get these mode values more often than you would get the overall mean. So that's what we mean by misleading mean and median values. So let's back up here for this distribution and do a top hat. So let's go here. Okay, so here is our data points, our death, age at death. And we're going to ask some questions. Can these histograms be used to predict an individual's lifespan? Okay. Can these histograms be used to predict an individual's lifespan? Okay. Someone having trouble, or is this a stray login? I'm going to move on. Okay, so there's our yeses and nos. 79% say no, and that's the correct answer. Okay, good. So we've determined or decided that the histograms of age of death at death cannot be used to predict an individual's lifespan. So now you get to type in why you think that's the case. So why can't the histograms of age at death be used to predict an individual's lifespan? So try to use some of the words that we've talked about in this class, not necessarily today. Okay. Or just give your own words. We'll see what we get. I'm going to do a word cloud, and we'll see if the word I'm looking for shows up as most used. Okay, just a few more seconds. We can move on. All right, good deal. Anyone one more time? Okay, seeing no hands, we'll move on. All right, so I'm curious about this. Okay, here are the responses. Let's show the word call out. Let's see what we get. Okay, factors. There's factors, of course. Let's see. I found it. I found the word I'm looking for. Okay, let's see what does condensed text mean? No, let's see. Show counts. What is this? Okay. See, nobody gave us the exact answer, but let's look at some of the answers. More factors than age, of course. Okay. Okay, there's the word descriptive, but it says not descriptive enough, so we'll talk about that. Okay. It's, let's say the data is not misleading, that it's actually telling us, you know, we've got the histogram, so we know even by age that I'm at higher risk because I'm in my 50s, okay? But that's describing what? What are these histograms describing? They're descriptive. That's the key word that I was looking for. They're descriptive. But what are they descriptive of? Yeah. Yeah, that's what they're saying at each little bin. That's how many people died at that age, okay? But it's the whole population, isn't it? It's the descriptive statistics of the population. You don't know which bin you're in. You're an individual. And so it's not predictive. And this goes back to, again, not being able to use descriptive statistics to predict an individual outcome. Yeah, so we could predict the population outcome. We could say, well, there's probably not much that's going to change year to year. Our diet really doesn't change that much. Our habits don't change that much. Maybe over time they change, but from year to year, probably not going to change that much. And so the population statistics may not change that much, but an individual, who knows? You know, who knows? And so it's not predictive of an individual, but it is maybe predictive of the population as a whole. Because again, it's hard to see it, every individual in that population changing at the same time and having a radically new population statistic the next year. But individuals, you have no idea. And so that's, again, that trying to take descriptive statistics and apply them to individuals is a real tricky business. So let's see what else. Okay. Now, these histograms obviously describe different lifespans for men versus women. But are these differences statistically significant? See, you see a difference. The red and the blue curves are different. The populations are different. But are they statistically significant? Okay, does anyone need more time? It's multiple choice, so I'm not typing. Okay, seeing no hands, I'm going to move on. Okay, so here's our distribution of answers. And so we've got 1 on yes, women live significantly longer than men, and then 8 on not sure, need a t-test of equal means, and not sure, we need a f-test of equal variances. Okay, and so the t-test of equal means would be the ones that was testing the differences in the populations in terms of the lifespan differences. So it is the women's significantly shifted to higher values than the men. Now, statistical significance would be, again, that t-test of equal means. What's are we 95% confident that, I shouldn't have gone, what have I done? No, I don't have to do it again. No. Well, we can go back to we're fine. We got the answers that you guys asked, or answered. So let's go back to the notes because I have that in the notes. Okay, so turn off the browser and go back to the PowerPoint. Okay, so what do we mean by statistically significant? So if we did a t-test on the means of these two histograms, we would get the pooled standard deviation, the standard deviation for the men, the standard deviation for the women. So standard deviation would be like the width of this distribution. So that would be sigma men, and then the red one would be sigma male and female. So sigma female. And then the pooled standard deviation would be the combination of those somehow pooled. And then we would look at those means, and we would do that whole t-test and get an experimental value, and then compare that to critical value. And it would test to see if it was really just all one distribution, right? If there's a statistically significant difference between these distributions. They overlap so much that although you can see the difference, it may not be statistically significant. Because look how much they're the same. That's the same part, okay? And our eye is naturally drawn to the differences. We see these outer sides of it, and those are the differences. But the sameness is huge. The overlap is huge. So sometimes we can't look at a graph of the data or a box plot of the data and make a determination on whether they're statistically significantly different. Okay, we would need that t-test to tell us if there's a 95% chance that they're the same. That would be the null hypothesis would be that they're the same. And then we calculate a p-value for that, or this t-test, and say, okay, at a 95% confidence level, our t experimental is greater than our t critical, and therefore they're different. Okay. Now, personally significant, okay, that's a different question. So like this right here, this group of males and that group of females, that's 4 years difference. 4 years may be significant. It may not. That's an individual issue, but we're really, even in this largest difference, we're talking maybe 4 or 5 years difference. Okay. Even down here in the hundreds, like here's 100 and here's 103. Okay, 100, 101, 102, 103. Okay, so you see that big red stripe and you say, oh wow, that's significant, but is it really statistically? You have to do the stats and get the numbers on it, not just look at the visual. Okay, so here's some other uses of some of the tools in Minitab. This is sort of leaving the let's see, how do I want to say this? This is, I guess, an effort to turn the descriptive statistics into a predictive tool. Okay. So you're still going to be talking about the population, but we want to look at what we call process capability. Now, I'm not sure that this is used in forensic science. I haven't found examples of it. It's definitely used in industry. So since we're talking about taking descriptive statistics and how would we use them in the future, we would want to maybe analyze how a process works. So let's apply it to our trainee and our forensic chemist as far as our cocaine samples. Now we have to sort of set up an artificial specification limit. And so we were analyzing cocaine, and we need, for this process capability, we need some specification limit. So let's just say that at 10% cocaine, below this is no charge, right? And above this is charged with crime. Might be possession or whatever, So do you see the specification limit? At 10% cocaine, if we analyze these samples and they say, okay, they were all below 10%, there's no charge for the crime. Now, that sounds crazy. Well, 10% kind of high, but I just picked it. But you've probably got cocaine in your pocket right now, every one of you. Where is it in your pocket? Money. It's coated on our money's coated in cocaine or heroin or mostly cocaine. You can find it on almost every bit of money that we have. And so they could detect that and put you in, you have possession, okay, of a controlled substance. You have control of that controlled substance. So it's in your pocket, right? But its amount is important. Right? Is it free cocaine, or is it something that's a residual amount on your money? Okay, so there is a sort of a precedent there that you might detect it, but that doesn't mean there's a charge. So that's our scenario here. So we'll say this 10%, whatever that is the cutoff for no charge if it's below that, and charge if it's above that. Now we know that the true value that we put into this analysis was like 13.2? I think it was 13.2. Yeah. So it was right here. That was the X true value, or our value that we put in. And our trainee was a little bit biased low. Their mean was lower than that. And their standard deviation was pretty poor. So they had a wide distribution. And look at the tail of that distribution. So if this trainee analyzes those values that should result in charge with a crime. So all of them were 13.2. Look what's going to happen down here. False negatives. You see what we're looking at? This is the capability analysis, and we're saying if given a sample that has 13.2% cocaine, with the uncertainty that our trainee has, they're going to have some false negatives. Now, how many would they have? This is it right here. The parts per million lower than the lower specification limit. So out of a million analyses, they'd have 972 that were false negatives. So this is a nice tool in Minitab. You can put your data in there and you can see if you have a specification limit, how many times you'll bust that limit. Okay, that's really fantastic. So this is telling us, so million analyses. I mean, that's a lot, but this is a lot of false negatives too. So that's 972. 72 over 1 million. Okay, which is equal to 0.09%. Okay, and so that would be, out of 100, they'd have to go to out of 1,000, they'd have like 9. That's not good. Okay, let's look at our forensic chemists though. Their precision was so much better. Okay, there's still the same check sample. 13.2 was our true value here. Okay. They analyzed those 10 times. Here's the mean and standard deviation they've got. And so notice their precision is so narrow, and here's the lower specification limit, that it's rounded down to 0. I mean, they're not going to have any false negatives at 10% cocaine with their precision. That's fantastic. So a million samples, they have 0 false negatives. As long as the samples were 13.2, they could even get down here. So how low could they go before they had an acceptable amount of false negatives? So you might say, well, we want less than 1 in 1,000 chance that they would have a false negative. Maybe that's not good enough. Maybe you say 1 in 10,000 chance, but you could set that up, and then you could slide that curve down until this false negative tail was 1 in 10,000. And then that would give you sort of this gray area. If it's in this area here, you would say, well, we're not going to make that call. We're not going to make that judgment. We're going to say it's too close to the low. So you might set up your own specification limit. Like if this is the legal specification limit, you may want to resample or do some other kind of analysis if you get below this mark, because you're getting too close to your unacceptable false negative rate. And so this is, again, just analyzing your processes, knowing when you're getting too close to the customer specification, and being afraid of having wrong results when they're going to, like in this case, have impact on someone's lives. Now, this is some real data that we collected in the lab. This was cleanliness data, and just showing you, just some more statistical graphs. This is a dirty part, so we put water drops on the surfaces to measure their cleanliness, and so here's the contact angle that we measure here. And so if the water wets the surface, it's a clean surface. It's a metal surface that has an oxide layer. Water will wet that surface and give you a low contact angle. And so we're looking at this. Here's the dirty contact angle. So, it's greater than 90. Let's say greater than 90 degrees is dirty. Okay, and so these are the initial data values. We did 24 measurements on these aluminum coupons, and then we got them dirty with grease. And so this is a gross contamination of grease, and so we see that the data has moved up to over 100 degrees. There's some that are as low as 80, but most of them are 100 or above, and so that's what we would call a dirty coupon. You could see the grease on the aluminum metal. Then we took a chem wipe and we wiped all that grease off completely. I mean, it looked beautiful. It looked really clean. And then we put the water drop on, and this is the wiped, still above 100. So we wiped the bulk of the grease off, but in the grooves and over the oxide layers, we still had a microscopic level of grease. In fact, contact angle can detect almost like a sub monolayer of contamination on grease. It's incredibly sensitive. But notice how the data really narrowed up because we had a uniform surface. So in our 16 measurements, they were all very close together. And so then we put it in the ultrasonic bath and with some detergent, we cleaned that off, and now our contact angle is better than it was. So it was sort of averaged around 60, now it's around 50. And of course, we could do that capability analysis with this. If our customer said we must have a wetting contact angle, so this is 90 degrees. So up here, these parts would be unacceptable. And these would be acceptable. Okay. We could calculate the process capability. When we take this tail out, how many of those samples, if we measured 1 million of them, would be measured incorrectly as being greater than 90 degrees? How many rejects would we have from our customers? What is this useful for? Well, this would be for coatings and things like that. If you're going to come along and paint that part, you need to have a bare oxide layer. If you want your paint to wet the surface, if there's any kind of grease or oil or fingerprints, then you're going to have a failure. It's not just for aesthetics either, for paint, but for transmissions. The company, a fellow engineer that was at Ford was telling me that they were analyzing their warranty recalls, and they put all this effort in cleaning the particles out of the internal workings of the transmissions and everything, and yet their warranty recalls were because the external gasket failed. Like the simplest place to clean on the whole part. They were really doing a great job of cleaning the really hard parts to clean, and then the exterior was still dirty when they installed it. And so then they went around and started adding contact angle to measure the cleanliness of that gasket surface so that it also held. And so that was kind of interesting. It was like we focused on the really hard stuff and we let the easy stuff slip for a little bit. And then they changed their process and they're back in the range where they want to be. So just a little bit of looking at these graphical statistical methods and looking at some of the vocabulary that goes along with them. So y'all have a good day. We're done a little early. So.